Teukolsky. We're lucky to have with us today Professor Saul Teukolsky of Cornell and Caltech. Professor Teukolsky is the 2021 recipient of the Einstein Prize, and the citation is for outstanding contributions to observational tests of general relativity with theories of gravitational waves, astrophysical black holes, and neutron stars. So he's going to tell us something about his work today.
Thank you. Please feel free to ask questions during the talk. You don't have to wait till the end. Since this is on Zoom, I can't keep track of the chat or people raising hands. So if somebody who's online sees that, please just interrupt me. But otherwise, you can unmute yourself and interrupt me in the middle of the sentence. It won't bother me. So so let me start by listing my collaborators. In particular, I want to single out Matt Giesler, who was a graduate student of mine at Caltech, who did the work on overtones that I'm going to talk about, which underlies everything that I'm going to talk about. And also Max Easy, who was a postdoc at MIT, who is mostly responsible for the data analysis that I'm going to describe. Okay, so let's start with this well-known picture drawn by Kip Thorne about more than 30 years ago. This was before we could solve Einstein's equations using big computers to describe very precisely the gravitational waves that come from two black holes that spiral around each other and merge with a nice big burst. And so we divide this gravitational wave into three regimes. The first one is this in-spiral region, where initially the black holes are far apart, and the waves that are being emitted can be calculated, so that's why it says known underneath, by doing perturbation theory about the Newtonian orbit. So you start with Newtonian physics, and then you add corrections from general relativity and powers of V over C, and then you can make a prediction. But eventually, velocities approach the speed of light, the gravitational fields become very strong, and we have this merger regime where the two black holes actually form a single black hole. And you see this sort of artist's impression that Kip drew of the complicated waveform here at this point. And then the final remnant black hole settles down quite quickly, radiating away the last sort of remnants of gravitational waves, and ends up as an isolated, rotating black hole in equilibrium. And this is also labeled known because this can also be described, this phase, by perturbation theory, but this time it's perturbation theory about the Kerr metric, which is the exact analytic solution describing a stationary rotating black hole. In fact, it's a little bit ironic for me. My PhD thesis was actually doing this perturbation theory and figuring out how a black hole does, among other things, settle down to a final state. And quite honestly, I've never dreamed that anything I ever did in general relativity would ever have any practical significance in the real world. That shows you. Okay, this is the first, these pictures here are from the first gravitational wave event detected by LIGO. this GW 1509-14. So in this top left panel, we see the strain, namely the change in the arm length of the detector, the fractional change, that was detected at the detector in Hanford in the state of Washington. And then on the right, the same strain detected at the other detector at Livingston, Louisiana. And so that's in blue. And then what the LIGO collaboration did was they took the red waveform and basically superposed it on top of the blue one. And you don't have to do any fancy statistics to tell that it's the same event, right? And since the two detectors are thousands of miles apart, that gives us confidence that they're actually seeing gravitational waves. And it's not just somebody slamming a car door in the parking lot or some terrestrial event like that. So in the second row, what the experimenters did was they did some smoothing of this waveform, filtered out some of the noise and so on. And if you look carefully, you'll see the gray lines there. That's the same information in the top panel, but now with the smoothing applied. And the width of the gray is supposed to give an idea of the uncertainty that comes from the noise in the measurements. And then superposed here, the red is actually a gravitational waveform. You see it says numerical relativity. That comes from our collaboration solving Einstein's equations with a set of parameters, a mass of each black hole and a spin for each black hole that best fits the data. And you can see from the goodness of fit here to the numerical relativity, that's how we know that this signal came from black holes, right? Because we set up a solution on the computer of Einstein's equations for two black holes merging, and this is what we get. The third row is the residuals. So you take the best fit in this numerical relativity best fit and subtract it from the top panel, and you get this residual. And this is consistent with Gaussian noise, right? So this is how we know that this is a very good model. In fact, the size of the residuals is about 4% of the amplitude in the first row. So if there are violations of general relativity, we know that at least in this kind of an event, they're not huge, they're probably less than 4%. Now, there's another kind of test that the LIGO collaboration did with this data, and that's a kind of consistency test. From the in-spiral part of the waveform, so this first part up to including the peak, so the in-spiral and the merger, you can, from that part alone, you can deduce the two masses and the spins of the black holes with some errors. Those can be input to the numerical relativity simulations, which is what gives you this nice fit in the second panel. And then the numerical relativity predicts the ring down phase. And from the data alone, you can fit what's called a quasi-normal mode. And I'll talk a little bit more in a minute what that means. But basically, it's this exponentially damped sort of sinusoidal piece at the end here. And as we'll see, that depends only on the final mass and spin. So you can compare what you get with this exponentially damped quasi-normal mode at the end of the waveform, that mass and spin, with the numerical relativity prediction for the final mass and spin given these initial masses and spins. And that fits pretty well. I'll show you in a few minutes what that what that fit looks like. Okay, so let's talk about quasi-normal modes. So a stationary black hole is described in general relativity by the Kerr metric. It depends only on two numbers, the mass and the spin, right? The angular momentum, J. In principle, you could have also a charge on the black hole, but we don't expect astrophysical black holes to have any significant charge because they're not in vacuum, they're in very dilute plasma, and any charge would get neutralized very quickly. And Wheeler coined this aphorism a long time ago, a black hole has no hair, to describe this, right? So it's not like the Earth or a star, where in principle you could have a whole series of multiple moments describing the shape of this object. The multiple moments of the Kerr metric all depend only on the mass, the monopole moment, and the spin, the dipole moment. And then all the higher moments are just functions of those same two parameters. This, by the way, is not necessarily true in other theories of gravity. And here's this picture from 1971 of all kinds of stuff going in to make the black hole, and all that information is basically erased, and all you can tell in the final state is the mass and the spin. And some of the younger people here may enjoy this nice picture of a 1970s television set. Okay, so this theorem that a stationary black hole is described only by mass and spin, right, is called the No-Hair Theorem. And one way of testing it would be to measure two of these quasi-normal modes that you get in the ring-down phase of the black hole. So each quasi-normal mode is just a damped sinusoid. So there's an exponential damping, a damping time tau, and a frequency for the ringing part. So an omega and a tau. And these are properties of the Kerr metric. You can calculate them essentially analytically. So if you can measure two quasi-normal modes, you would have four numbers, two omegas and two taus, that should depend only on the mass and the spin. And so that is a test then of whether the No-Hair theorem is respected or not. And when this idea first was proposed in the late 1990s, early 2000s, when LIGO was just getting going, the estimates were that given the sensitivity that LIGO was expected to have, even at its design, which it hasn't quite reached yet, the signal to noise ratio would be too low. You wouldn't actually be able to do this test. You would have to wait for sort of the next generation beyond LIGO, things like Cosmic Explorer and so on, or possibly even LISA, a space-based gravitational wave detector, which we hope will launch in about 2034 or so. So this was a very sort of interesting idea, but people kind of put it on the back burner. So let me describe why this idea was wrong. So this is about the only real slide, maybe 1.5 slides. I'll have some equations. So let me talk a little bit about how Kerr perturbations, this ring down phase, are described analytically. So you have this rotating black hole. It's axially symmetric. So if you make perturbations, you would expect to be able to separate variables in the azimuthal coordinate. And you can see here, there's a superposition over the m quantum number, e to the im phi, to represent that dependence on phi of the perturbations. Also, because the background is independent of time, you can separate out the time dependence. Here's e to the minus I omega t. You can see there's just a Fourier superposition. But for the r and theta dependence, you would not expect, there's no particular symmetry. You wouldn't expect to be able to separate variables. And a big surprise is that, in fact, the r and theta coordinates, if you do this with the right variable, this variable I'm talking about, psi 4, is a particular combination of curvature quantities for the perturbations of the Kerr metric. And if you use the right quantity, there's a miracle, and you get the separation of variables. So these angular functions are called spin-weighted spheroidal harmonics. You can think of them as just glorified YLMs, glorified spherical harmonics, because they depend on A, which is the spin parameter related to the angular momentum of the black hole. And then the R is like the radial part of the wave function. And so, for example, when you have a spherical black hole, a non-rotating black hole, it obeys a kind of a barrier penetration, you know, these problems you see in elementary quantum mechanics. It looks just like that. And then when you go to the Kerr metric, so it's no longer spherically symmetric, all that happens is the potential depends on the spin and the frequency. It becomes complex. But conceptually, this is just like a quantum mechanical barrier penetration problem. And then it turns out that this quantity psi 4 here lets you calculate the strain, the H that LIGO detects. Basically, psi 4 is just 2 time derivatives of the strain. Okay, so that's all you need to know about Kerr perturbations. In fact, you don't even need to know that, because we're going to focus on what happens at late times. So the late time behavior of R is you get these damped sinusoids. So you get behavior e to the minus I omega with a mode, a frequency Lm and n. So the frequency of the mode depends on the Lm, on which harmonic you're talking about. And then there's an n, which is like a radial quantum number that comes out of the radial part of the equation. Okay, so you have this outgoing mode, and that the prediction is that LIGO should see just a superposition of these. So if you decompose this into modes, let's just replace S by YLMs. It's a detail. Technically, you can just it's possible to do this exactly, but conceptually, just think of these as YLMs. So for each L and M that LIGO detects, you should see a sum over these overtones, these N's, these radial quantum numbers, and here's the damped sinusoid. So the omega is complex. It has a real part and the imaginary part. Okay, so this is just copying from the previous slide. So the omega is complex. There's a frequency, a cosine omega t, and then a damping time in e to the minus t over tau. So you should see a superposition of these. So this n is called the overtone index, and according to the No-Hair Theorem, these frequencies should be functions, since this is the Kerr metric, only of the 2 parameters, the mass and the spin of the final black hole. Okay, and by convention, we label these overtones in order of their damping times, right? So the fundamental is the least damped mode, so the one that should last the longest. And then as you go up in n, you get less and less, you get things that are more and more damped. Now, for a long time, people ignored these overtones. And part of it, I think, is because calling them overtones was a poor choice of name. When physicists talk about overtones, the first thing that comes to mind is, music. You have a violin string, and you put your finger down and you pick out a fundamental tone, and then you get overtones which are harmonics of that frequency. And their excitation is typically subdominant. They give some color. They let you distinguish a particular note played on a violin from the same notes they played on a clarinet. Okay? Black hole overtones are completely not like that at all. They are not multiples of they're not overtones in the sense of being multiples of the fundamental frequency. And they needn't be subdominant. So this confused people, I think, for a long time. All right, so here is a figure from this paper, 2016 paper of the LIGO-Virgo collaboration. And it shows their consistency test. So plotted on the horizontal axis is the frequency, the real part of the quasi-normal mode frequency. And on the vertical axis is the decay time, right, the damping time. And so this contour in the middle, the solid contour, is the prediction for the fundamental frequency, which is the L equal to 2 quadrupole mode, L equal to M equal to 2, fundamental mode, the N equal to 0, like the longest lived overtone. And so this comes from doing this in-spiral merger ring down consistency test, where from the in-spiral merger part, you get the initial masses and spins. You then use numerical relativity to predict what the final mass and spin of the remnant black hole should be. And then you look up what the prediction is for the quasi-normal mode. And putting in the noise in the measurement, you get this small contour in the middle. Then what they did was they fit one single damped sinusoid, right? So cosine omega t e to the minus t over tau. They fit that to the ring down. But now the question was, where should they do the fit? So these times that you see, 1 millisecond, 3 milliseconds, and so on, those are times after the peak of the waveform. And the idea was you have to wait long enough, right? Presumably the peak comes from the merger event, which should be highly nonlinear, right? Because you need numerical relativity to actually calculate what's going on. Then you have to wait a bit for the nonlinearities to radiate away until you're in that last stage where you're dominated by this quasi-normal mode. Okay, so for example, here, this contour, this green contour is waiting only 1 millisecond. And you can see it's completely biased. It doesn't even enclose the true value. Waiting 3 milliseconds at least encloses the small contour, although it's biased. It's nowhere, the center of the 3 milliseconds is offset from the center of this small contour. If you wait 5 milliseconds, you can see that's now less biased. But on the other hand, the noise, the signal itself is damping exponentially. So you're much more sensitive to the noise in the detector. And that's why the contour, the error that's allowed, like these, I think, are 90% contours, is much bigger. And you can see if you go 6.5 milliseconds, it's just completely swallowed in the noise. So this led to a whole literature on what's the optimum strategy here. When does ring down start? When should you do the fitting to optimize for a given event to try to do the best job of picking out this quasi-normal mode? Okay. So we're left with the question, when does ring down start? At what point do you transition from this nonlinear merger to the correct, into the description in terms of quasi-normal modes. So the problem then is here we're plotting, these are I sort of glossed over the fact that there are two polarization states, just like an electromagnetic wave. So the two polarizations in the strain H are shown in these different colors here, and there's an envelope to the waveform. So where should we start trying to fit a damped exponential or a sum of damped exponentials? And the zero here is taken relative to the peak of H. For the experts in the audience, I just want to point out that there's a difference between describing the peak of H and describing the peak of psi 4 because they're related by two time derivatives. So we're talking about the peak of H. Okay, so here is the answer, and this was the big surprise. You can, if you include the overtones, you get a very good description of the late time behavior of the wave, as long as you include the overtones. The nonlinearities don't seem to play a big role in what an observer at infinity who's measuring the strain sees. Okay, and this was like a revelation to people in the field. Now, actually, my graduate student, Matt Giesler, who I mentioned, he was not the first person to notice this. Way back in 2007, which was the Stone Age as far as doing accurate numerical calculations of black hole mergers, Bonanno, Pretorius, and Cook did a numerical simulation where they were able to pick out, they looked at the peak of psi 4, and they were able to show that using 2 or 3 overtones gave a good fit to their data. And this was actually used in what was called the effective one-body model, the semi-analytic model that LIGO has been using to do its data analysis. But for various reasons, people kind of forgot about that. The EOB model was used more as a, some kind of a heuristic fitting model for the data, and so its origins in this were kind of forgotten. All right, so let me convince you of this fact. So what we're looking at here is a very accurate, completely numerical solution of Einstein's equations. Right? So this is the numerical, the NR waveform. And we fit that with a superposition up here, the first line, a superposition of quasi-normal modes. So you can see we're just fitting the 2-2 part against the numerical, the accurate numerical waveform. And so we have an option, the T0 is the start time relative to the peak. And capital N is the overtone number that we choose to keep. So what's plotted on the horizontal axis is the start time. And the vertical axis is the mismatch. So that's computed basically, you can see down here, it's just an overlap integral, a dot product, just like you do in quantum mechanics, between the exact solution, the numerical relativity waveform, and the approximation as a superposition of normal modes. So a small number, a low mismatch, means you've got a very accurate fit to the numerical waveform. So the blue curve, the first one, is just fitting the fundamental. And you see, provided you wait, a reasonable time after 0, after the peak, you get a reason, maybe 10 to the minus 3, 10 to the minus 4 error in the fit. But then as you start adding more and more overtones, the mismatch goes down, and the time at which the mismatch gives you a good match, I mean, the mismatch is low, you can see goes down to 0, maybe even a little bit before 0. And the only reason we stopped here at n equal to 7 was we were now hitting the error, this was the accuracy of the numerical wave. Okay, so this is kind of the evidence that overtones work. So the nonlinearities are small. Here's another way of showing that data. You can see by eye, you can't see the difference between the numerical relativity waveform and the n equals 7 fix that's plotted on top of it. So on the bottom panel, we've subtracted them and shown the difference. It's sort of between 10 to the minus 4 and 10 to the minus 5. And then in blue is an estimate of the accuracy of the numerical waveform, and it's below 10 to the minus 5. So that's a surprise. This is my favorite way of showing the data, what's going on. So what we've done here is we've taken the best fit, right, with the n equals 7, and then we take each mode, we take its amplitude then at t equal to 0. So that's what's plotted on the vertical axis. Okay, so at t equal to 0, we plot the particular amplitude, and then as t goes on, we show the exponential decay, the e to the minus t over tau, multiplying the amplitude it had at t equal to 0. So that's the exponential decay of each individual mode in the sum. And this blue one that survives at late times, that's the n equal to 0. That's the fundamental. And you can see how you have to wait sometime after the peak before that's a good representation of the waveform. Right at the peak, the waveform is actually dominated by some of these n equal 3, 4, 5 overtones. Their amplitude is bigger than the fundamental, but it just decays away. They decay away more rapidly. And that's why what people thought was nonlinearities was actually a linear superposition of these so-called overtones. Okay, and that's what was going on. The units that we use here are units of m, the total mass of the system. And the way to think about it is the Schwarzschild radius, say for a spherical black hole, is 2m in these units. If you put in the speed of light and the gravity Newton's constant and so on, then 10m, which is when the fundamental is dominant, for the first event detected by LIGO is about 3 milliseconds, which is empirically what we saw LIGO had to wait for to see this particular mode, this fundamental mode, be present. So everything now is consistent. Okay, so when we put out the first paper on this, some of our colleagues were not very impressed. They said, well, you're just fitting a whole bunch of dense sinusoids, with enough parameters. Each one has a complex amplitude and the complex frequency. That's 4 numbers, and then you're fitting 8 overtones. That's 32 parameters. So of course you get a good fit. And some of the mathematical types pointed out, well, dense sinusoids are not a complete orthonormal set. They're actually overcomplete, blah, blah, blah. Okay. Well, that's nonsense, okay? So one way to think about it is quasi-normal modes arise in any wave equation where the that effective potential, that barrier penetration potential, falls off. There's certain mathematical conditions. As long as it falls off at infinity, there's a Green's function then that you can use to predict the response. And in particular, it gives you the late time behavior with these quasi-normal modes. They turn out they're just poles in the complex plane for the Green's function. And they give you the asymptotic expansion. So what you're really doing is you're fitting your observed data to the poles of this asymptotic expansion. And the asymptotic expansion is not a complete orthonormal set. It's whatever it is, right? It's an asymptotic expansion that we know from the Green's function representation. So fitting has got nothing to do with having complete orthonormal set. Then there's also been some literature, even as late as 2 days ago, there was another paper on the archive talking about the instability of quasi-normal modes, and they dress it up with pseudo spectra and all this mathematical hocus pocus. Again, I'm not impressed, okay? We take the exact, quote, exact nonlinear solution of Einstein's equations with a numerically determined complete waveform, and we fit with the predicted asymptotic expansion, and it fits perfectly. So anybody who's claiming that there's some instability that they justify by some perturbation, pseudo-spectrum, whatever, the onus is on them to explain why we fit the data so well, right? It's not for us to explain why our fitting is not unstable. So another way of saying it is, my attitude is mathematics is an experimental science, right? So empirically, here's what happens, and then the mathematicians can fiddle around to get it right. So let me elaborate on what I mean by saying mathematics is an experimental science. So let's consider an experiment where instead of using the analytically known values for these overtone frequencies, we'll perturb them a bit, right? So we take the true values, these omegas, so the 2 overtone values, and we multiply them by some arbitrary factor here with the delta. And we try then to fit for the final mass and spin. So we take damped sinusoids, but not with the true values of omega and delta for the overtones, but just some randomly chosen ones. And all these different lines here, so the blue is the original using the true values. This is the vertical axis is some measure of the error in the mass and the spin of the fit. For no good reason, I used chi here. Chi is another symbol that people use for the spin. All the other lines correspond to different recipes for doing the perturbation. So, multiplying everything by a fixed numerical factor up to 20%, random, things distributed with Gaussian profiles and so on. And you'll see that they're all worse. They all give you a bigger error in estimating the final mass and spin. Only when you use the true values do you get the best fits, the best possible value. So that's what I mean by saying experimentally we know that these are, quote, the right values for the quasi-normal mode frequencies. Okay. Let me skip that slide. So now let's try to do a real test of the No-Hair Theorem using real data. And up till now, what I've been showing you for our work has been justifying by fitting to a very accurate numerical relativity determined waveform. Now we take the LIGO data and we try to fit the mass and the spin with quasi-normal modes, but we'll do the fit instead of weighting. We're going to fit at the peak of the waveform. So what's plotted here is the final mass and the final spin as determined from the quasi-normal mode frequency. So the x in the middle is the, quote, true value. So it comes, you see that the dotted line is from the in-spiral merger ring-down test that I mentioned earlier, where you fit the whole waveform, not just the last part, and assume general relativity is correct. You get a centroid and then some noise. The blue curve, n equal to 0, so you can see this one is completely non-centered on the true value. That's the biased value you get when you try to use just the quasi-normal fundamental mode to fit to the data. And the reason it's way off is because you haven't weighted. That's not the dominant representation when you try to fit at the peak. The orange curve includes one overtone. And you can see already that gives you something which is reasonably centered on the true value, right? It has some contour giving the error. If you try to add another overtone, it stays centered, but now there's too much noise in the data, in the real data. Just remember, you're not trying to fit to a very accurate numerical waveform. So what this suggests then is that in the data, you have very strong evidence for the fundamental and one overtone. And another way of representing this information is in these corner plots. So let me show you how to interpret these. What's shown here is, again, we'll try to make a perturbation, right? So we'll take the real part of the frequency, the F2 for the n equal 1, and we'll perturb it. And we try to do the fits for the data, right? So how consistent is this data with a delta F of 0 in that fundamental mode, right? So that would suggest then it's consistent with general relativity. So if you look at this information here in the bottom left plot, you can see that there is, as you move away from delta F equal to 0, but there's a contour. This is sort of roughly at the, it's a 90% confidence. The data sort of would be consistent with a 20% deviation from 0 at 90% confidence. Okay, so you have, I wouldn't say it's an overwhelming test, right? But it's saying that this data, which remember comes from the very first detection of a gravitational wave event, when LIGO, this was in the first observing run, we've just completed the third one. So if an event like this were detected in, say, the next observing run, 04 next year, when the signal-to-noise ratio would probably be roughly 3 times what it was for this event back in 2015, you would probably be able to see 3 or 4 overtones and do a much stronger test. Okay, but even with this so-called lousy data, you already have a crude test of the No-Hair Theorem by seeing 1 overtone in addition to the fundamental. Okay, let's talk about the area theorem. So Hawking's area theorem says that the total area of all black holes cannot decrease. Now, what's the area of a black hole? Well, we have a simple formula, again, for a Kerr black hole. So this would be a black hole at rest, in equilibrium, not time dependent, and just described by its mass m and its spin, right? And so this is the area A for such a black hole. And at first sight, it seems preposterous. How could you ever test this theorem, right? You'd have to find some black holes, presumably, widely separated, so you can treat them as isolated, somehow measure their area, then, come back later after they've interacted in some way, measure the area. It seems crazy you could ever do it. Well, you can, because we can measure the masses and the spins of the initial black holes, and hence from this formula get the area, right, for each one and add it up. And then if we can separately analyze the ring down part of the waveform, we can get the final mass and the spin using the quasi-normal modes, and then we can test whether the area has in fact increased, or at least hasn't decreased. So the key to being able to do a test like this is to be able to do a separate analysis of the in-spiral part and the ring down part, right? Because in the earlier LIGO test, what they did was they used the in-spiral part to get initial masses and spins. Then they used a numerical relativity calculation to predict the final mass and spin. But that doesn't test the area theorem, because as soon as you use numerical relativity, you're using Einstein's equations. And of course, if you use Einstein's equations, you're guaranteed to get to uphold the area theorem, right? Because it's general relativity. So what you want is a separate analysis of the initial black holes and final black holes. Okay, so that's a little tricky, because normally when you do parameter estimation, you do it in frequency space, right? There are a couple of reasons for this. One reason is the noise spectrum of LIGO, which is used in the data analysis, is known, is measured as a function of frequency. And also, for efficiency reasons, you get to use some fancy data analysis tricks, FFTs, and so on that you can do in the frequency domain. So you can see the challenge here. I've drawn a blue line on this waveform. So if you wanted to separately analyze, say, the first part and the second part of the waveform, you can see that if you try to Fourier transform this, there's a discontinuity, right? There's a sudden, at the peak here, you suddenly have a non-zero value, right? Compared, say, with a zero value at the end point, or for the in-spiral with a zero, in the early time. So, if you Fourier analyze something that has a discontinuity, you get Gibbs phenomenon. Okay, so you'd have lots of high frequency noise if you did the data analysis in the Fourier domain, right? So, for theorists, let me explain how this is handled. I'm sure all the experimentalists are bored by this description, but right, what one does in the Fourier domain is you apply a taper to the waveform, which basically smoothly turns on the signal from zero to get rid of the Gibbs phenomenon. But that's not very good here, because if you apply your taper too early, say before the peak, then you're contaminating the merger signal, the ring down signal, with some of the in-spiral merger signal. So it's not a clean separation. And if you apply the taper too late, then you're throwing away some information where the signal is strung in the ring down. So the trick is to actually do the data analysis in the time domain. And if people want to know how you do that, you can ask me in the question period. There's some neat stuff that Max Easy figured out how to do that. Right? But let me just say, you do the analysis separately for the in-spiral and for the ring down in the time domain. And here's what you find. Okay, so what the plot shows on the horizontal axis is the fractional change in the area, right? So the final black hole area minus the sum of the initial black holes divided by the initial. And on the vertical axis is the probability. So let's look at the green curve. So that's using the one overtone, n equal to 1, just as we did for the quasi-normal mode, the no-hair test. And 0, so to the left of 0, the delta A is negative. So that means that the area has gone down compared with the initial value. And you can see there's a small probability, the area under the green curve. And that area is about 3%. So with 97% probability, we can say from the data, Hawking was right. The area of a black hole, some of the areas of the black holes does not decrease, even in this very nonlinear merger event. And presumably with upcoming events that will give us much better signal to noise ratio, this will improve. Okay, so let me summarize. What have we learned? So despite the highly nonlinear nature of the merger event, as far as the waveform that propagates out to infinity, you can understand that strain waveform as a superposition of linear superposition of quasi-normal modes, which include the overtones. Okay, and so they dominate the early ring down, but describe everything from the peak of the strain. Right? So the nonlinearities in what's observable at infinity are presumably very small. You don't see them very easily. And these overtones enable a test of the No-Hair Theorem. We're not going to have to wait for space-based detectors, and similarly for the area theorem. So thank you very much. I'll stop there, and I'm happy to answer questions.
Well, thank you for an excellent colloquium. There will undoubtedly be some questions from various people. So I'll just pause and let those who want to ask questions just basically unmute yourselves and speak one at a time.
Is now the time to speak?
Yes, go.
Yeah, Saul, you said that, of course, this was an enormous surprise that this works. And it seems to me such an enormous surprise that it's hard to believe that anybody looked into it. And so maybe you could tell us, how did that happen, that somebody thought this could be true? And then my other question is, given that this is true, what's your current understanding of what it tells you about Einstein's equations and how this merger is occurring?
Right. Okay, so the first thing is so this is a good example. You know, there's this sort of apocryphal, you know, this belief that you know, young people make all the great discoveries, right? And you know, it's not completely true, but there is an element of truth to it. And I think part of the explanation is that, young people haven't been prejudiced or biased by all of the information that they've accumulated. So in the case of Matt Giesler, one of his fellow graduate students was working on a project to determine what was the optimal time, what was the right time when ring down starts, where you should do this analysis and you would be in the linear regime. And Matt was very accomplished at generating numerical waveforms. So he thought, well, I'll look for myself. And he didn't know any better. So when he fitted the damped sinusoids, he included the overtones because nobody told him not to. Nobody said only include the fundamental. And so, he came into my office one day and he said, look at what a good fit I get if I include the overtones. So that's what happened there. So what does that tell you? So that's very interesting. My suspicion is what it's telling us is that the final black hole has this sort of effective potential around it. And perturbations that are sort of close to the horizon have to do a sort of a barrier penetration thing to get out to infinity. And the effective potential must be kind of forming relatively early in the merger process and sort of screening. The nonlinear information is presumably falling into the black hole, and very little of it is leaking out. And the stuff that's leaking out is this quasi-normal mode superposition. So that's my picture, my mental picture of what's going on. But, it could be completely wrong. So you should take that not, with a wheelbarrow of salt. I mean, it's really just a mental picture.
So let's see. There may be other questions. All right, let me ask.
Hey, Kevin.
Yes.
Kevin, I guess I have a question. This is Rich. So I got a little confused. So initially you showed a plot showing 7 overtones, a fit with 7 overtones. Later on you emphasize 1 and maybe 2. So I was just wondering, how many are significantly detected?
Right. So the difference was in the first part when I was showing sort of very high accuracies, mismatches of 10 to the minus 6 or something. That was fitting a superposition, including overtones, to a numerical solution. So, and the numerical solution was computed with high accuracy, because it's just how long are you willing to wait for the computer, and what kind of resolution are you willing to use. The fit with 1 overtone was to real LIGO data.
Okay.
And that's contaminated by noise.
Right.
And so you can't push down. If you try to include more overtones, the noise kills you. And you can only pick out 1 overtone.
1, okay.
That's the difference, yeah.
All right. Then I had another question, which I may have missed you saying. So this was all fit to the first event, is that right?
That's correct.
Okay, and that's the one that's giving you the most information so far?
Yeah, so it turns out that the LIGO is now detected of order roughly 90 events in the catalog that just came out of, I guess, Sunday night. The latest catalog was announced on the archive. And this earliest event is still the highest signal to noise for doing this kind of test. But it will be interesting because what you could do in principle is try to combine data from several events and maybe get a slightly stronger test. But that's going to take us a little bit of time to do that.
Right, yeah. Okay, thank you. Wonderfully lucid talk. Thank you.
Thank you.
I do have another question. Given what you can do with the current LIGO detectors and with this wonderfully serendipitous first event, what could you tell us could be done with the upgrades to LIGO and then with the planned Einstein telescope and Cosmic Explorer? What could we learn from those?
So in this particular test that I focused on, I would say that LIGO at design sensitivity, right? So whether we'll get there, 04, so that's the fourth observing run, which is now scheduled for starting in December next year. I'm not sure whether they'll be quite at design sensitivity then. So it may only be the run after that, another year or two later. If you had an event that was as strong as this first one, I think you'll easily see 3 or 4 overtones in that. So you get a very good test. I'm not sure which will come next, whether it's going to be the next ground-based detector after that, Cosmic Explorer or something, or whether it will be LISA in space. LISA, the signal to noise of LISA should be, probably 100 times better for, now we'll be talking about supermassive black holes merging. Just a huge increase in the accuracy. And we'll be doing exquisite tests. If there's any deviation from GR, that's at 1% or so, or even sub% level, we're going to see it in these kinds of tests. There are other tests too that can be done, but in particular in these kinds of tests. So it's exciting.
Let's see, maybe there are more questions. Maybe I'll ask a super elementary question while others are thinking about phrasing their questions. This business of the total area of the black holes increasing, is the idea that the entropy is proportional to the area and the entropy has to increase? Is that the basis of it, or does it actually come from Einstein's equations?
Yeah, so it was
I
actually
guess it must, but
yeah, so it's actually the other way around, right? So the area theorem sort of came first, right? It's a geometrical statement, and uses Einstein's equations as part of the proof. But of course, it was motivated by these ideas about what happens to entropy, right? If you throw stuff, stars, you have a star which has a lot of entropy, it's hot and all kinds of things, and then you collapse it into a black hole, you've decreased the entropy of the universe. So where does the entropy gone? And what the area theorem let us do was generalize thermodynamics to include black holes. So the idea was, if you added the entropy of the black holes to the entropy of ordinary stuff, you could maintain the second law of thermodynamics. So that was sort of the motivation for these things.
thank you. So I don't hear any more questions. Maybe we should just thank you again, and I guess we could send you an email. People could email you a question.
I'd be happy if people want to email me. That's fine.
And so let's give a final applause, and thanks very much for doing this.
Thank you.
And congratulations once again on being the recipient of this year's Einstein Prize.
Thank you.
And I hope we all avoid COVID.
Thank you.
Okay, well, Ed is controlling the recording and so forth, so